Okay, all right, so let's get started. So today we are going to talk a little bit about machine learning. So let's start with my favorite TV show. All right, it's called Sherlock. I don't know if anybody watches Sherlock on PBS, BBC. No, if you don't, please do watch it. It's done for this season, but I think you can find some older episodes there as well. So Sherlock is on PBS, starring, of course, Benedict Cumberbatch and Bilbo Baggins. And the reason I'll tell you why I'm talking about Sherlock today. Of course, Sherlock is based on Sherlock Holmes, who was created by Arthur Conan Doyle way back. And one of the aspects of Sherlock Holmes was his art of deduction, right? So he could deduce things. He was a very famous detective. I hope everyone is familiar with Sherlock Holmes. But anyway, so one thing he was known for was his art of deduction. So he could deduce things and figure out who committed the crime and so on. But there was one, of course, the Sherlock show is a little it's adapted from that basic, from the original stories. So in one particular show earlier this year, there was a time when Sherlock was able to sort of predict what's going to happen next, especially to his colleague, Dr. Watson, right? And Watson was very puzzled, and he asked him, like, how can you predict the future, right? And he said something that kind of caught my eye, which is that if you could bring together all the necessary data elements, right, you can process it in a right way, you can predict what's going to happen next, right? And I thought that was pretty interesting. Of course, what he was doing was pretty insane, but in general, I think that is one of the core reasons why AI and machine learning these days is so useful, because people have realized, of course, humans can't do all of that, right? Humans cannot bring in all data. Maybe Sherlock Holmes could, but ordinary humans cannot put together all the data and make predictions in the future. But people have realized that we can have machines do that, especially now when we are able to collect different types of data together, right? So that, I think, is one of the reasons why these things are so popular these days, because now what you can do is you can bring all this data together and predict when somebody is going to get sick, or when is somebody going to click on certain ad, or what is somebody going to buy, or when is someone going to commit a fraud, and so on, right? So these are all interesting applications of machine learning these days, and the reason they are so important, or at least the market thinks they are so important, is because they're in some ways trying to predict the future, right? So we will see in this course how we can predict the future, but of course, within some scope and everything, right? So I don't know if any one of you got a chance to. So one of these very cool applications of trying to predict the future. When I say future, it's not just future, but anything that's not apparent, right? So you want to know something about something. How can you do that without really, going forward in time? Yeah. So one of the applications, of course, I told you about this this article in New York Times. It's called "The Grand AI Awakening." So if you get a chance, please look at it. But it kind of talks mostly about language systems and how the modern language translation systems are very advanced, right? So even if you go to translate.google.com, you type something in English, very almost real time it translates it into many languages. So for example, if I enter the title of that article, it translates it to French in real time, and it does a pretty good job, right? For example, things that sort of caught my attention was the fact that it was able to put New York Times as New York Times instead of translating new into French and Times into French, because it knows that New York Times is itself an entity, right? So these are the things that are possible because of some of the machine learning algorithms that go inside. Yeah, and we will sort of learn about some of them as well. And I don't know if you, some of you might have taken course in information retrieval, and there are certain aspects of that here as well. All right. So now let's go back to the basics. So yeah, on Monday I told you a brief background about machine learning, right? How it is a branch of AI, right? So AI, of course, started way back in 1950, late 1950s and early 1960s, where people started to ask the question that can we make machines think or behave like humans, or essentially exhibit intelligence like humans, right? That's what is called artificial intelligence. This was after, people were comfortable with computers. They were pretty fascinated. These computers could do everything. So they said, hey, how about we make them act like humans, right? And then there were a lot of initial systems that were out there. Of course, all of you are young, so I don't know if you are familiar with toys like these. So this used to be a pretty interesting AI system. And you will see that it's actually pretty basic, but at that time that used to be the state of art. So it was called Eliza, and you can talk to her, right? So you can say hello and it would answer, right? So she's trying to imitate humans. So that's a example of artificial intelligence, but very soon you'll see that it kind of breaks up. So for example, if I say, what is the answer to question 4, it will say, why do you ask? So it is still kind of acting like humans, but it's not very useful because it has some core responses inside and just gives you those responses. It does a little bit of parsing and understanding what kind of question you're asking, but very soon you'll see that it starts to break up, right? So if I say, why am I sad today, it will say something that's similar, right? So the idea is that the reason I'm showing you this is because just the fact that a machine can imitate humans is kind of not enough to call it an artificial intelligence system, right? For example, sometimes, when kids have this phase, right? Sometimes I talk to my daughter and she just says the same thing back, right? So you can create a simple machine that can do that, right? And it kind of imitates my daughter, but it's not really an artificial intelligence system. What you really want in an AI system is some utility, something that can help us with, right? So that there are all these questions there. Okay, how do we define it, and so on. Of course, so that was a question that people came up with back in 60s as well. Is what do you call an AI system? And then there were some tests that were proposed. One of the popular tests was called Turing test, named after, actually developed by Alan Turing, who's also known as the father of computing. And there was another movie about Alan Turing last year, I don't know if you got a chance, called Imitation Game, also starring Benedict Cumberbatch, incidentally. Anyways, so that was more about cryptography, but he has done a lot of work in AI as well. So he came up with this test called the Turing test, where the idea is that if you want to figure out if a machine is human or not, or an entity is human or not, what you do is you stick that thing into a room, stick a human in another room, and outside there's a third judge who asks both things questions, right? And let's say those questions are, there's some other human inside who can input it to the machine or the human, and then the answer comes back and that human sort of calls out the answer, right? So if the judge cannot distinguish which one is human, which one is not, then it is an AI machine, right? So that was a simple test. Of course, there are all kinds of controversies over that. The example that I gave, where if I put my daughter in one room and the machine in another, and they are both repeating the same thing that I am saying, it would pass the Turing test, but it's not really an AI machine. So there are all these interesting questions there. So if you're interested in sort of general AI and the philosophy behind this, we can talk more. It's not part of this course, of course, but I thought it would be nice to sort of start with that. All right, so then we need to understand, where does machine learning fall into, right? So when we are talking about intelligent machines or AI systems, there are broadly 4 things that we want them to be able to do. All right, one is ability to take in input from the surroundings, so ability to talk, ability to see, ability to hear, and process it essentially, right? To make sense of what is coming inside. So that's what humans do very naturally, and we want machines to do that. And each one of these capabilities are actually a topic within AI and computer science, right? So there is computer vision that talks about how to see, speech recognition, language processing, and so on. The second thing you want the system to do is the ability to store all the information that is coming in. Store and access it, right? So areas like information retrieval, semantic networks, ontologies, they deal with this knowledge representation aspect. Third is the ability to reason, right? to decide. So you want a robot or an artificial machine to make some decision. Okay, if this happens, I'll do this. If that happens, I'll do that, and so on. So that comes under mathematical logic and some Bayesian inference stuff. And the fourth thing that we want that machine to do is the ability to learn over time, improve over experience, right? And that is where machine learning falls into, right? So that's why I say that machine learning is a part of AI, and it is one branch within AI, which essentially deals with how can we make machines learn over time, right? And we will define it a little more. So let's talk about, okay, so of course we are trying to create a machine that can imitate humans, right? So let's talk about human learning and then see how we can translate it into machine learning. So as humans we learn, right? When we are born, we don't know much, right? But over time we do learn, right? Kids learn to walk very fast. They learn to sit up and then recognize their parents and laugh and cry and so on. So those are things that we learn, right? However, those are very complex tasks, right? The current state of machine learning is nowhere near human learning. So we try to simplify things that we can make a machine learn. So one thing that we say is we can make a machine learn concepts, right? And that's kind of what humans do as well. So for example, slowly a child learns to identify chairs, right? So in the beginning, if I say, what is that? The child might not know. But slowly, if I say, where is a chair? The child can point to that, right? So we in machine learning call that concept learning. Learning to define something, right? So I show them an object, they can assign a label to that. Another thing that we want machines to do is to distinguish between concepts. So essentially say, is this a chair or a table, right? So we can do that. So we want machines to do that as well. There are other things that we learn too, right? For example, we learn a language, we learn how to use our phone and so on. Those are things that are still sort of a little away from what machines can do. So in this course, we will be more talking about concept learning, concepts and distinguishing concepts, not these other things, which eventually we want to. I mean, there are systems that have learned language. So for example, that translation system, of course, is something that knows a language and so on, but we won't go into that here. Then the other thing is, how do we want the machines to learn? So to do that, we first want to see how do we learn, right? So we learn in many ways. One is, of course, we learn by going into a classroom where somebody is telling you what things are, right? So you can come to a classroom and I can tell you that this is a table and this is a or that is a chair, right? And then you say, oh, okay, you go back and go back with that knowledge. So that's called passive learning or teaching. The other thing is we can learn through experience. So you don't go to a classroom, but what you do is, let's say how. So let's say you're trying to distinguish between chairs and tables, right? So what you do is you just pick up an object and you say, this is a chair, right? And then you take it to somebody and that person gives you $1 if you are right and takes $1 from you if you are wrong, right? So as you keep doing this and keep making mistakes, you will start to learn more. You say, every time I took something which had arms, the person said it is a chair, I got $1 back, right? So that means that anything with an arm is most likely a chair. And every time I took something which is more flat, then it's a table and so on. So that's how we learn over with experience, right? So actually in machine learning, in this course in particular, we will primarily focus on that, learning through experience and learning through these examples where you get some reward and then you kind of try to improve to maximize your reward, right? There are other ways to learn as well. So another way is to learn through queries, right? So for example, instead of having a teacher who tells you, you can have a teacher or an oracle, but what you do is you essentially pick up an object and take it to the teacher and ask him or her, is this a chair? And based on what they say, you try to revise your sort of learning, right? So that is called learning through queries. We won't look at that this time. Another is learning through experimentation, which is also kind of similar. So that's again, for example, that's how kids learn how to walk. How to walk, maybe. Yeah, that's how kids sort of learn a lot of things. So for example, a kid when she's very little would go and maybe touch something that is sharp and they get they get hurt. So next time they know that shouldn't touch that thing. So that's kind of learning through experimentation. Even animals learn like that, right? If you have pets at home, you will see that pets sort of pick up things through experimentation. They try something and something works, something doesn't, and that's how. So I don't know if you can think of some of the machine learning algorithms that we'll see here as some sort of experimentation, but I would more focus on learning, active learning through examples. All right, any questions so far? All right, very nice. Okay, so moving on. So of course, we are computer scientists, so we like to define things, right? So in computer science, there are exact definition of machine learning as well. So just another background story is that one of the first machine learning programs or algorithms was created by this American researcher called Arthur Samuel. He used to work at IBM. So in 1959, he created this machine which could play checkers with him. So what he did was, he liked to play checkers, of course. So he created a machine, and in the beginning that machine was pretty dumb. So Arthur Samuel would win every time. But slowly what happened was that, I mean, he programmed it like that. So slowly that machine started to learn, and after some time it started to beat him. Yeah. So that was, I mean, people call that as the first machine learning algorithm. I'm sure there were many more before that. But anyway, so if so that's just a bit of history. But if you look at Tom Mitchell's book, right? So he defines he provides an exact definition of machine learning, right? So what is machine learning? He says that machine learning is defined with respect to a program, a software that you write, right? So a computer program is set to learn over time, right? If there is some notion of an experience, so the machine is getting some experience to do some task. So there is a task involved, there is some experience involved. So we are not talking about people that imitate humans. So I don't know if you've watched Blade Runner and movies like those, right? So you have or Terminator. So there's a person who is exactly like humans, but we are far away from that, right? So right now we keep it very simple. We say there is some task that needs to be performed. There is and only one task, and there is a system, and the system is experiencing something, and over time it improves how it performs that task. So that is called a learning machine, right? That's a very general definition. Okay, and then so the next question is why, right? Of course, with the example of Sherlock, I gave you a very vague motivation for this, but there are precise definitions for this as well. Like, why do you need machine learning, right? So if you go back to AI, right, why not just stop at machines that can do 1, 2, and 3? And a lot of current robotic systems actually just do 1, 2, and 3, and they're fine with that, right? But the thing is, the reason we want learning machines is because then we can let them we can create a small machine which doesn't know much, just like what Arthur Samuels did, and then just let it be, and then slowly it accumulates only the right amount of knowledge, right? I don't know how many years that was, but it was 5 years ago when they had this IBM Watson, the computer, compete against some human champions of Jeopardy, right? And eventually Watson won. Right? So what Watson was a classic AI system. It could take questions as input, and it could process information inside and give you the answer, right? It was pretty good at that, and it won, of course. But if you looked at what Watson was, so if you ever get a chance to go to TJ Watson Research Center in near New York City, Watson is a huge machine, right? It occupies half of a basement. It needs a lot of cooling. There's all kinds of infrastructure inside, right? So the reason it was that big was because they made it. They put everything in it. They made it sort of know everything, so that when it goes to Jeopardy, it can, whatever answers were asked from it, whatever questions were asked, it could give the relevant answer, right? But the problem with those machines is that they would just like Watson be huge, right? Because they are trained to do everything. However, if you look at Tom Mitchell's definition, you want the machine to do a certain task and be good at that, right? So you don't want to train it on everything, right? So that's why if you have systems which you can create very small systems, and then slowly they understand what is needed to perform that exact task. They won't be that bulky, right? And they'll improve over time. And the other issue is that, of course, you cannot program that initial machine to do everything. There might be something that you miss, right? What if in future that is the thing that you experience? How do you adapt to that, right? So a non-machine learning AI system won't be able to adapt to that, but a machine learning system maybe will fail, but next time it will adapt, and so on, right? So that is sort of a general motivation. Another example I gave is this the Deep Blue machine. Long time back, there was a contest between humans and computers in playing chess, and there's a machine called Deep Blue, also developed by IBM, and it played Garry Kasparov, who was the world champion at that time. And so there also, I think, I don't know, I think it was a draw or something, but that machine was also huge. It was a supercomputer pretty much, right? So you don't want machines like that. You want machines like Arthur Samuel built, a small piece of code which eventually wins, right? So that is the idea. And then, of course, so the idea is that machines that can learn will be compact, because they will only learn what is necessary to them, and they can adapt to new situations. And of course, they are based on certain assumptions, which we will look at as well, which is that whatever you experience in future is not too different from what you have been trained for, right? So if I train a machine to distinguish between chairs and tables, right, but tomorrow I show it an elephant and ask it to distinguish between elephants and tigers, it won't be able to do that, because there's not much relationship between elephants, tigers, and chairs and tables, right? So there should be some sort of a relationship, structural relationship between now and future, and so that's sort of the core assumption. Any questions so far? Okay, so moving on. Of course, there's a very nice example of one such system, which is called Kiva, which is it's kind of a robot. Doesn't look like a robot. It's used in these warehouses, places like Amazon, where it learns to sort of navigate these huge warehouses and put stuff from one place to another, and so on. So when you get a chance, you can look at this video, but it's another sort of very interesting application. All right. So the reason I introduced Kiva was just to give you an example, right? So for example, so how do we make a machine learn, right? So the first thing, of course, is what do you want it to learn? So for example, let's say, so you have to define that. So it's not, we are not yet at a stage where you can just create a program, just say, go learn, right? That we are far away from that. But if we tell that, okay, this is what you want to learn, so right now we have very good systems to do that. So for example, let's say Kiva, right? So Kiva was this warehouse robot, and we want to make it sort of distinguish between tables and chairs, right? So how would we go about doing that? So the first thing we wanted to do is we want to tell it what typical tables look like and what chairs look like, right? So now how do we provide that information to the robot? That is the first step, right? We cannot input the table into the program, so we need to represent the table as some representational features, right? We call them features which describe some characteristics of that object. So for example, now how do these what do these features be? What should these features be? They should have some things that help the machine distinguish between the two things, right? So for example, if you want to distinguish between tables and chairs, and let's assume they're all made of wood, then the characteristic that made of wood is not a good feature, right? Because tables are made of wood, chairs are made of wood. Or have 4 legs, again, is not a very good feature, right? However, if you have a feature like has backrest, that's a good feature because you can distinguish between the two. So you want to have, the first thing you want to do is, how do we represent our data, right? We call them features. Sometimes they're also called variables. I don't know why, especially when you come from mathematics, you call them variables. But from from more descriptive perspective, you have to call them features because they tell you something about the object. Sometimes people also call them, I don't know why they call them variables and dimensions, but anyway, features is a good word. Now, what should the features be? They should be computable. You should be able to compute it, right? There should be distinguishing between whatever things you are trying to distinguish, and they should be representative. It shouldn't be that you just for example, this chair, right? This is a little weird chair. So one aspect of this chair is that it has this sort of a V structure over here, right? But this is very unique to this chair, right? So if you create that as a feature, that would probably not help a lot, right? You want features that are common to a lot of these things. So you want those things, right? So that is the idea. All right. Of course, when I say computable, you should be able to compute that. So, for example, a feature which is a chair, right? That's of course an excellent feature, because if you know that, then you can distinguish between chairs and tables. But that was the first question, right? You can't compute it. Otherwise, why would you do this whole exercise, right? So they should be computable. All right. So that is the idea behind machine learning. So now let us look at how machine learning, what are the core assumptions behind machine learning. So I've given you two examples here. So examples of two types of logic, right? Remember, I was talking to you about Sherlock Holmes, right? So Sherlock Holmes was known for his art of deduction. So what is deductive logic? So on the left, there is, in fact, I would rather use my, this here, sorry. Okay, where are we? Right. So I'm going to give you an example of deductive logic. It's my giant pen. So if I give you a statement which says all birds can fly, right? And another statement that dodo is a bird, right? Then somebody can deduce from that dodo can fly, right? There's no issue about that, right? That's how humans sort of apply logic. That's very logical. No problem. Sherlock Holmes would have no problem with that, right? But what if I give you another example, which is a stingray can swim, right? Stingrays can swim. And the second statement which is true is stingray is a fish, right? Based on these two, I make this inference that all fish can swim. Is that logical? Does that look? There's something wrong with that, right? You're trying to generalize based on one observation, right? So that is what we call inductive logic. Yeah. So of course this seems correct, this seems completely wrong, right? But it turns out that machine learning is based on this logic, inductive logic. You're trying to generalize from little, right? And and that is sort of the first thing that you want to understand, the notion of inductive logic. Because all we do in machine learning is to go from little. We see a few tables and chairs, and then we basically make judgments about everything else, right? In real life, you are told not to do that. That is what we call stereotyping or profiling and so on. But machine learning is all about that. We encourage it to do that, right? So that is the idea. So inductive logic is the core tenet in machine learning. Any questions about that? And we'll look at this more and more later, right? So the idea is we induce from past, not deduce, right? Because deduction is easy, but if you can deduce, then you don't really need all of this sophisticated machinery, right? Because if you know all birds can fly, then that's logical, right? That will go in the third part, which is decision making of AI systems. But inducing from the past is less exact, but that's what you want to do, right? That's what we do as well, right? We see some things, you see 4 or 5 faculty members and you see they are awesome, and then you induce that all faculty members must be awesome, right? So that kind of example. All right, so that is the idea. So now let me sort of show you one example of a machine learning system, right? We will not try to understand how things are done underneath, but we'll just try to see how it is built, okay? And that will give you a sort of a general idea, and then we will jump into how to come up with algorithms and so on, right? So there is this very beautiful web page somebody came up with, and it's just, I mean, I just keep looking at it all the time. It's made in, you know, d3.js, so all these advanced JavaScript kind of, or HTML5 type of visualizations. But and so they do, I'll show that to you. So the problem here, the distinguishing concept here is you want to create a machine which can distinguish between houses in New York and houses in San Francisco, right? I don't know why you want to do that, but let's say that is the example. Yeah? So given some information about the houses, I want to distinguish between, I want to say, is this house in New York and is this house from San Francisco? What is given to me are a bunch of houses from New York and San Francisco, right? Now what exactly the way they are represented is you're given some information about them, like when were they built, how much do they cost, what elevation they are, and so on, right? You can also develop a system which can look at actual image, right, and distinguish between houses in New York and San Francisco. But in this example, we won't do that. In your first programming assignment, you will do that, right? Not for this particular case, but looking at images, how do you distinguish between two types of images? That's what we will do in programming assignment 1. But today we're going to assume that what we are given is a bunch of houses, right? And we are given some features of those houses, and I'll show you what those features are, and also given the label, the truth about the houses, were they in New York or San Francisco, because you need that to learn, right? So that is the idea. And then let's see how it does, right? So when you look at this example, I also want you to compare it with how you would do that as humans, right? Let's say as humans, you have no clue about how houses in New York look like, or what they are, and what houses in San Francisco are, but you, based on that data, you want to do that. So what you will see is that humans and machines kind of go in a very similar fashion. So let's go to this web page. It's called Visual Introduction to Machine. Oh, sorry. Make it big. Yes. Right. So forget about what is written over here. This is actually a more description of how decision trees work, which is one of the machine learning algorithms, which we will not cover. But I want to use this to sort of explain how sort of general machine learning is done, right? So the problem is, using a data set about homes, we will create a machine learning model to distinguish homes in New York and San Francisco. So the first thing and we call that problem as classification. You want to classify an object into two or more categories. Here we are looking at two categories, San Francisco or New York. So that is called binary classification. But in some, if you have multiple, you call it, you know, multi-class classification and so on, right? So the first thing you want to figure out is, okay, what feature should we use, right? So the first feature that they use is the elevation of the house, okay? So what you see here is each row is a house, okay? All the blue houses are from New York, all the green houses are from San Francisco. So what you see here is that if you just look at the elevation as the feature of the house, we see that a lot of San Francisco tends to have very houses which are at higher elevation, right? The New York elevations are low. So this could be a nice feature to distinguish, right? However, it won't be exact. So for example, if I choose a threshold of 240 feet, right, which is actually just over the highest house in New York, and say that anything over 240 feet is a house in San Francisco, that will give you some good performance, but not quite, right? Because there are a lot of houses in New York which are also, San Francisco, which are under 240. But you can treat it as your first machine learning model, right? It's just a simple test, right? You just say if height greater than 240 feet, assign label as San Francisco, right? So that's your first model. It won't be very accurate, but it will be reasonably good. But now we say that, okay, how do we want to improve this, right? So the way to improve is that you add another feature to it. So for example, you can add, let's say, the price per square foot, right? So the one question that you should ask me at this point is, how am I picking these features, right? Why did I take height first and then I took cost per square foot, right? So, and that is an art in machine learning. Getting the right features is the most important part, but it is also the least well understood part. Usually these are the kind of information that comes from the domain experts. So maybe a real estate developer, right, could tell me that, hey, you should look at height and you should look at price, right? So let's say this is given. So now if I look at the data, right? So now what I have done is that instead of looking at the data in along one feature space, I'm looking at it in two. So each dot here is a house. This axis, this x-axis, is the price per square foot, and this axis is the elevation. So now what you see is that you get a much cleaner picture, right? So now what you can see is that if I call houses which are greater than 1800 per square foot and less than 100 feet, I will call all of them as New York houses, right? Because all of them pretty much are in New York. And then houses that are here, I'll call all of them as San Francisco. So you can create another conditional statement in your machine learning algorithm, and now suddenly you have an even more improved algorithm, right? It's still not perfect because you would make a lot of mistakes on these houses because they are mixed up, but you are sort of doing better, right? So essentially what you do in your code is you draw boundaries by doing that if else. That's what you're doing. You're saying if house price is greater than this and elevation less than this, call it a New York house. If house price is less than this and elevation actually just greater than this, call it this house, and so on. So that's how you sort of improve your classifier. But now you want to do even better. So what you do is you add more features. So in particular, in this data set, there were 7 different features that were available. Okay, so there was, it's hard to see. So right here it is, right? So there's elevation, year it was built, number of bathrooms, bedrooms, price, so on. So now suddenly you are representing your data in 7 feature space, right? That's why they call them dimensions, because suddenly now you can think of putting your data point into a coordinate space with 7 dimensions, right? We can see 3, but in principle you can have any, right? So let's say you have a 7-dimensional space, hyperspace. You can put your data points there, and you can create these rules so that you can differentiate between different types of points, right? And so these plots are actually just 2 by 2. So this is comparing elevation to year built and so on. But now we want to develop a machine that can come up with these rules, right? So one of these machines is what we call decision tree. And what you will see is that that's exactly, well, not exactly, but that's also how humans try to learn as well, right? So what happens is, so in the beginning, of course, we had this, right? We said we only represent data using elevation, but slowly we said let's look at the distribution, right? So this is what we call an empirical distribution, right? So that's also a very important concept you need to be familiar with. So if I give you a bunch of numbers, right, and I ask you to tell me how they are distributed, one of the easiest way is to draw a histogram, right? You divide the range into some fixed number of bins, and then you count how many fall in each bin, and you plot it, right? That's a very interesting, well, it's a very intuitive visualization tool, and it is also very important. We will see that later as well. So if you draw the heights of houses as a histogram, you can now see where should I put my boundary, right? I can put my boundary over here and say any house above this is San Francisco. Houses below this, I'm not sure. I need more information, right? So that's how we also sort of do as humans. Then we can say, let's look at these houses. What is another boundary we can draw? So for example, what we can do, of course, if we had chosen some other boundary, then we wouldn't have done so well, right? So if we choose the boundary as 240, what happens is that all the houses on this side are San Francisco. You're doing very well. Houses here, you're not doing well at all. So you need to do something about this. But if you choose your boundary to be on little more on the left, then you won't do well in either case, right? So for example, look at this guy. It's very sensitive. Okay, sorry, but anyway, so depending on where you set your boundary, you will do good or bad. But now you can add more information. So let's say you set your boundary here. You say this is a point where I'm making some mistakes on this side, I'm making some mistakes on this side, but overall this is the least amount of mistakes I do, and then I can find more distinguishing features in each side, right? So then you add something else. For example, let's say you add the price. Now suddenly you say, let's first look at a house, see what its elevation is, right? And then either send it to this branch or this branch. Then let's look at the price, and if the price is above certain number, then go to this branch and this branch, and keep doing that until you can figure out, okay, what class this is. So at this point, I don't want you to really fret over this, that you don't understand how it works, because that's sort of how decision trees work, and we're not going to cover it here. But intuitively it makes sense, right? Because that's how, as humans, we also tend to work. When we see a lot of houses, the first thing we want to do is, because every human tries to minimize the chaos in our mind, right? So the first thing we want to do is, hey, I see that half of the San Francisco houses are over this height, so let me use that as my first sort of feature, saying, okay, if I see a house over this, I'll call it San Francisco. Now for these other houses, let me also look at the price, and then and so on. You keep doing that until you build this entire tree in your mind, right? And so that is the idea. Beautiful tree, right? So the idea is that now I get a new house, I can sort of follow these, and these you can implement as a logical steps, right? Just if else statements. You can just go and figure out, what is it, New York or is it San Francisco? So this is kind of your first machine learning model, right? You can learn it, and I'll not tell you how to learn it. There are ways to do that, but once you learn it, then you can use it in future, right? So there are two phases in machine learning. There is a learning phase where you actually learn this or something else, and the other is the actual phase where you use it, right? Sometimes we call it testing, sometimes we call it the predicting phase, where you get a new house and you don't know if it is New York or San Francisco, and then you sort of go into it and figure out what label it is, right? So we'll look at both of those things. So eventually what you want to do is, once you learn this model, you get new data, and each data point, based on what their features are, they kind of go into their respective classes. Yeah, very cool. So this is at least I really like how they put this together. But this is sort of your first introduction to a machine learning system. Any questions so far? All right. Okay. So that kind of concludes the first part. Essentially, I don't think I had anything else. This is the reference to the paper that talks about the Turing test. It's just called Mind. So it's an interesting read if you get a chance. Anyway, so let's quickly move to part 2, just to get sort of started with it, and then next class we can get. All right. So now you have some idea of what machine learning is, and what is essentially the task behind machine learning, right? And so there's a notion of some data, which there's notion of a learning phase. In machine learning, we also call it the training phase. So you take the data, and there is some program that you train on this data, right? So it kind of improves itself, and then at some point you use it to make future prediction. Yeah. So we will look at, so the way we will do this course is, we will start very simple. We will start with very simple assumptions, and then we will sort of branch out, make it more interesting. So there's notion of data, right? Then the notion of the learning, and the notion of prediction, or classification, or basically an output, right? So depending on, so now I don't know, I showed you a list of a lot of algorithms that we are going to sort of look at, right? So the one question that might come into your mind is, why are there so many algorithms? Why is there not just one algorithm that works for everything? And the reason is because the entire problem is nuanced. So it's not like there is one problem, right? So of course, one of the things is that the data can be of different types. Sometimes you might have images, sometimes you might have just features that we saw, you might have text, you might have something else, right? So there's so much variation in the type of data. So one algorithm cannot handle everything. So what we will do is we will start with a very simple assumption about data, okay? And I'll talk about what that assumption is on Friday, but we will make some very simple assumptions so that we can sort of understand this more, right? The second thing is, what are we trying to learn, right? Are we just trying to distinguish between two types of classes as we did for that home example, or are we trying to predict something? Are we trying to predict what will be the temperature of Buffalo tomorrow, right? Which will be certainly below 20 Fahrenheit. Are we trying to do that? So depending on what we are trying to do, it's going to be a different thing. The other thing here is, so what are we predicting? What are we predicting, right? Is it one number? Is it a class? Multiple classes, right? The other thing is, what is there in the data to learn? So as we said in the house example, right? We already had this data which told us where was this house from San Francisco, was this house from New York, and so on. We call that data as labeled data, right? So we can have labeled data, but sometimes we might not have labeled data. Sometimes we might just have bunch of data objects. I might just have information about all of you, right? But I have nothing really to predict, but I still want to infer something from this, right? So that is what we call unlabeled data, and we call that kind of learning unsupervised learning. So the last part of this course will focus on unsupervised learning, but the first three parts will mostly focus on labeled data. But depending on if we have labels, if we do not, we will have different types of learning. So that's why we have many algorithms there. Then prediction, right? What are we trying to sort of predict? Are we trying to predict exact number, or are we trying to predict some confidence bounds in our prediction, and so on? So what we predict also, sorry, this should be what are we learning, and this should be what are we predicting, right? Then there are other complications that arise as well. For example, what if the data has some corruption inside, right? What if there's some noise in the data? For example, in that New York, San Francisco example, somebody had measured the elevation of these different houses, right? What if there is some errors in those measurements, which typically happens, right? You can't have very precise measurements. How do you handle that noise, right? What if by mistake a New York house was in the training data was labeled as a San Francisco house, right? So what if there is noise or errors in the data? So we have algorithms that can handle that as well. Yeah. So the other complications are noise and error. So we will later on sort of look at algorithms that can deal with this issue as well. But on Friday, what we are going to do is focus on a very simple setting where the data is very simple, and I'll tell you how it is simple, and there is no noise, no error, and all we are trying to do is distinguish between two types of things. Yeah. So that is what we call concept learning, and we will do that on Friday morning.